Lasserre Hierarchy.
Thanks for having me here. So I'm going to talk about new tools for graph coloring. As you all know, graph coloring is you assign colors to vertices so that no two adjacent vertices will have the same color. Well, in general, this is a very hard problem. You can't hope to approximate the number of colors in like n to the 1 minus epsilon. But so in a special case where the graph can be colored with a small number of colors, so when the graph is 3 colorable, means the graph can be colored using only 3 colors. There are algorithms that can use few colors to color the graph. As you see, there's a line of work starting from Wiggerson's algorithm in 83. It gives O tilde square root and coloring. Here, O tilde always hide logarithmic vectors, so it can always color a graph with square root n log n colors. Later, Karger, Motwani, and Sudan give an SDP algorithm that can color any 3 colorable graph with roughly n to the 1/4 colors. And an improvement over this is given by Blum and Karger, and it gives roughly n to the 3/14 colors. This is already like n to the 2.2 something. And since then, progress has been slow. Until 2006, Sanjeev, Moses, and Eddie, they gave a new algorithm that is actually the same as KMS and Blum Karger, but they used better analyze for the SDP. And they were able to get this n to the 0.2111 colors. So finally, Eddie improved this by using constant runs of Lasserre hierarchy to get n to the 0.2072 coloring. Well, so in this talk, we are going to talk about even more special case of this. So we are not going to improve over these exponents. So our work actually follows from follows the line of work started by ABS. So Sanjeev, Boz, and David. So they have an algorithm for unique games that runs in sub-exponential time. And the key idea is if the graph has low threshold rank, then this graph is easy for many of the problems. So, so in particular, we'll show this theorem. So if this graph is regular, it's also 3 colorable. And also it has low threshold rank. I will define threshold rank later. So rank of minus, say, 1/16 of G is equal to D. This is essentially the number of eigenvalues that are smaller than minus 1/16 is D. Then there exists an algorithm that can find independent set of size at least n/12. So this is a really large independent set. It's linear size. So if you can find such an independent set in every graph, then you can apply this algorithm iteratively. And at the end, you will get logn coloring. This is done in n to the order of d time. In particular, it requires to solve Lasserre hierarchy SDP for some constant times d levels. So, so the definition for threshold rank, this rank, some minus constant of G, is defined to be the number of eigenvalues that are smaller than minus C, where so eigenvalues are in this range -1, 1. So they are eigenvalues of the normalized adjacency matrix. But this is actually different from the definition of threshold rank in ABS. There they are interested in eigenvalues that are close to 1. So their definition is what we denote by rank 1 minus epsilon of G is the number of eigenvalues that are greater than 1 minus epsilon. But here we are actually interested in eigenvalues that on the other side of the spectrum.
So you want to remove one negation?
What?
You said we were referring to the number of eigenvalues smaller than -16, right? Yeah. So you want to remove one negation. Oh, you wrote minus one.
Oh, I wrote minus C. So this is just tell you that we are interested in negative eigenvalues instead of.
I missed the negation in front of the one.
Yeah. Oh, sorry. There's a negation here.
So this is of the adjacency matrix?
Yeah, of the normalized adjacency matrix.
Normalized,
yeah, so eigenvalues are all in +1, -1. So.
Is it really it doesn't work, or you don't know if it works if it just has an independent set of size 1/3?
No, 1/3. Well, actually, I think it can, using the current proof, it can go at best to n over 6.
No, I mean for the hypothesis, can you weaken it from being 3 colorable to having an independent set of size n over 3?
No, it has to. So it has to have a solution for so many rounds of Lasserre hierarchy. It's not enough to have just a large independent set. Yeah, so the hypothesis is actually a bit weaker than what I wrote here, but just having a large independent set is not enough. So how do we usually apply threshold rank? So why does threshold rank help algorithms? So actually, we don't know many examples, but most comes from the paper ABS. So one thing is if threshold rank is low, this is slow, then then you can use this eigenspace enumeration. So basically, you enumerate all the vectors in this space spanned by all the large eigenvalues, and hopefully there's something you want that is very close to this space. In particular, you can find you can approximate small set expansion. So if this is D, then also you know that there exists a set S with edge expansion equal to, say, gamma. Then you can find an S prime, which is very close to S. So the symmetric difference between S and S prime over the size of S is at most gamma or epsilon squared. So this is proved in ABS.
So this is using epsilon s.
Yeah, this is using epsilon s over the space spanned by low dimension, spanned by high eigenvectors. Yeah. Also, if threshold rank is high, there's something.
Maybe do you want to differentiate the two definitions just so that we're not confused? This is dead. This is closer to 1, right?
Yeah, this eigenvalues that are close to 1. So right before our work, no one has considered negative eigenvalues. So all those works, they work with eigenvalues that are close to 1. So another application is, so we know if threshold rank is low, we can do this eigenvalue enumeration. But what if the eigenvalue is, the threshold rank is high? So rank of 1 minus epsilon, G is actually very large. It's larger than, say, n to the 100 epsilon over gamma. Then what they show in ABS and also previously in a paper by Sanjeev, Russell, Matthews, and David. So if this happens, then the random walk of the graph cannot mix very well for small sets. So in particular, you can find a set S such that the size of size n to the 1 minus epsilon over gamma, and the vertex expansion of the set is at most square root gamma. So this is also proved in ABS and also earlier in this work. So right, this is essentially how in ABS they get an algorithm for small set expansion, because either threshold rank is low and you can apply this algorithm, or the threshold rank is high and you can find this set.
This actually gives you vertex expansion?
No, these are all edge expansions.
And what is the second paper?
So it's the paper before ABS by Sanjeev, Russell, Matthews, and David. It's also something about unique games. So this is one explanation of why threshold rank is useful for algorithms. But recently, so Boaz, Prasad, and David, they come up with an alternative explanation. So alternative. So this alternative explanation says that if the threshold rank 1 minus epsilon of G is high, it actually means it's impossible to have vectors. So vectors C1 to Cn such that well, expectation over an edge so this is saying expectation, the expected correlation between an edge is large. The inner product is larger than 1 minus 2 epsilon.
So what are the constraints on the ZIs?
Yeah, I will explain. No, they are expected unit vectors. So the expected length is 1. Yeah, I'll write the constraint later. Also, although this local correlation is high, the global correlation. So if you pick 2 random P and Q, 2 random vertices, then the correlation CP CQ, for some reason there's a square here, it's much less than 1 over D. So this is impossible, meaning if threshold rank is D and the vectors have high local correlation, then they must also have a high global correlation. Their global correlation cannot be much less than 1 over D. So in particular, they showed that this is relaxation for threshold rank. Relaxation for threshold rank. So you try to maximize this D, the threshold rank, and you want to find the vectors Z1 to Zn such that for a random vertex, the norm of the CP squared is 1. So this is just a normalization. And for random edge, CP, sorry, here it should actually be, instead of 1 minus 2 epsilon, it's 1 minus epsilon over 2. Anyway, so for a random edge, this inner product is at least 1 minus epsilon. And for a random pair of vertices, this correlation CP and CQ squared is at most 1 over D. So their claim is that this is a convex relaxation for threshold rank. And we'll see how this is proved. Yeah, before this should actually be half. But
You can use the right-hand word.
oh, okay. Yeah. So so to show that this is indeed relaxation for threshold rank, we we have the following lemmas. So, so if threshold rank is high, if rank 1 minus epsilon of G is D, this actually implies the optimal for that program is at least D. Later we'll have another lemma which says if threshold rank is low, then the optimal is also low. Okay, so the proof, so this lemma is simpler. So we know the threshold rank is low, so we just take the eigenvectors. So we let W1, W2 to WD be the eigenvectors with eigenvalues larger than 1 minus epsilon. So this, by this we mean, so G times Wi is equal to lambda I times Wi. And lambda I is at least 1 minus epsilon. Also, we normalize this by saying that the expected value of WIP squared is exactly 1. So because threshold rank is high, we have to have these eigenvalues. But now we need to construct the vector Z in this relaxation. This is done by, so we first write this W vectors as row vectors. So W1, W2 to WD. So this is W1, W2 to WD. This is W1, 1, W1, 2, W1, N, W2, 1 to W2, N, WD, 1 to WDN. So we write them in this way.
So this expected, I mean, are you just making them unit vectors with this?
Yeah, this is essentially unit vectors, but correspond to this expectation norm. So if it's unit vector, is this expectation is actually 1 over n.
Sorry, yes.
Yeah. So yeah, there's this difference in norms. Yeah, but anyway, so we write them as row vectors, but then we look at the column vectors. So this vector is what we hope to be Z1, and this vector is just Z2. And finally, this vector is Zn. There's still a normalization factor, so these are actually square root d times the corresponding z vectors. And we claim that these z vectors, they satisfy all the three constraints. Well, this is not hard to prove, so let me number those equations. So this is 1, 2, 3. So for equation 1, we are trying to compute the expectation over P. This ZP norm squared. But this is actually the sum of squares of all numbers in this matrix. So it's actually, we have this normalization factor 1 over d because here is square root d. and then the expectation over P, sum of I from 1 to D, WIP squared. Well, then you switch the sum with expectation, and it's clear this is just 1. So equation 1 is satisfied. Then you look at this equation 2. Equation 2 is just expectation over P over an edge, the inner product. Well, of course, you expand this inner product by a sum of, still you have the 1 over D normalization factor. And this inner product, after you open it, is sum of products of W. So it's sum I from 1 to N, 1 to D, WIP, WIQ. Now, again, you switch the sum and expectation, and I write the expectation in this way. So I first take expectation over P, WIP. Then I take random neighbor of P, WIQ. But as we defined, this W is an eigenvector, and this is you take one step of random walk from P to get to Q, and the average of WIQ. So this is exactly lambda I times WIP, because it's an eigenvector. Now you see this is lambda I times WIP squared. So this whole thing is just lambda I. So this is 1 over D times sum of I from 1 to D, lambda I. And as we assumed, all the eigenvalues are at least 1 minus epsilon. So this is definitely more than 1 minus epsilon. So 2 is also satisfied. Yeah, let me see.
Maybe erase the ones on the left.
Yeah. Well, so finally for 3, we need to compute expected value of random P and Q, this inner product squared. Well, because this is actually a degree 4 term, so the normalization factor is 1 over D squared. And you take expectation over PQ, the sum over I from 1 to D, WIP, WIQ squared. And you expand this squared, and you get 1 over D squared, expectation over PQ, sum of I and J, so WIP, WIQ, WJP, WJQ. Again, you do the trick by switching these two, and notice that P and Q are independent. So you gather all the terms with P and all the terms with Q. So this is 1 over D squared some I j from 1 to d, expectation over p, wi p, wjp, expectation over q, wiq, wjq. Well, as we define these w vectors, they are eigenvectors, so they are orthogonal to each other. If I is different from j, then this expectation is exactly 0. So I has to be the same as j. And when I equals to j, this is just the norm of this vector, so it's 1. So this is 1 over d squared, sum of I from 1 to d, 1. So this one is d, this is 1 over d squared. So this is exactly equal to 1 over d. And so optimal is exactly d. Well, so optimal is at least d, because we already show there's a set of vectors that achieves 1 over d. But the more interesting part is actually this direction, which means if threshold rank is low, then this third equation, the global correlation, cannot be too small.
You can erase the left one.
Well, you've got
Left top. Left top. No, left. All the way to the left.
Yeah, I think I'll just erase. Okay. But this one is actually harder to prove, and this word is not enough. But anyway, let's start here. So this lemma says if the threshold rank 1 minus 2 epsilon of G. So notice here is 2 epsilon instead of epsilon is low as D, then optimal is at most 4 times D. So this is a less trivial direction. The proof is kind of similar to that. Let's assume that we have this set of vectors z1, z2 to zn, such that they achieve opt. Notice that in these equations, we are just interested in the inner products of these vectors. So without loss of generality, we can assume they are like dimension n vectors. Well, there always exist such vectors, so that inner products are the same. Now again, like there, we write these here. This is C1. This is C2. And this is Cn.
Times root d again, or?
What?
Times root d again?
No, this time there's no normalization. So these are the these, and Then we look at the row vectors. So we call them x1, x2 up to xn. This n is actually not important, but n is always enough. We also need to think of the eigenvectors. So we let W1, W2 to Wn be all the eigenvectors. Again, we have the eigenvectors. GWI is equal to lambda I WI, and lambda 1 is greater than lambda 2 is greater than lambda d, which is more than 1 minus 2 epsilon, and all the rest are smaller than 1 minus 2 epsilon, as we assumed. Also, they are still normalized, so that this norm expectation over p WIP squared is 1. So now what we want to do is to show that these vectors better be the eigenvectors. So we are going to express these x vectors in the basis of the eigenvectors. So we say xi is equal to sum of j from 1 to n, alpha ij, wj. So we express them in the spaces, and then we want to see what zp times what's the inner product zp and zq. Well, now this is a bit complicated because we have zp zq is actually the sum over I from 1 to n, xip, xiq. But x is expressed in this spaces, so if you expand that, is sum over I from 1 to n, sum over j1 from 1 to n, alpha I j1, wj1 p, and another term was q, some j2 from 1 to n, alpha I j2, wj2 q. So as you see, there are well, actually n cubed terms, but we are just going to be interested in n squares of them. So when j1 is not equal to j2, you see this product will have wj1p times wj2q, and we know that wj1 and wj2, they are orthogonal. So for the first two equations, after we take the expectation, all those terms will disappear because they are all orthogonal. So let's just say that this is.
Maybe write a little bigger.
Yeah, let me write it also here. So zp, zq is equal to. So I'm only looking at the terms where j1 is equal to j2. Sum over j from 1 to n sum over I from 1 to n alpha I j squared. Because when j1 equals to j2, these two are the same, so you get a squared. Wjp wjq plus the rest of the terms. And we call this alpha j squared. And we will see that these alpha j squares have nice properties. Let me prove it here. So is it clear up to here? Okay. Now for equation 1, we compute this expectation over the norm squared of ZP. But ZP inner product with ZP here is just sum of alpha j squared times wjp squared. So this is sum over j from 1 to n, alpha j squared, wjp squared. Sorry, this is expectation over p. So you see expectation over p, the norm squared is 1. So this is just sum of alpha j squared, and it's 1. So these alpha j squared, they are actually like the weights for the eigenvectors. These terms will all disappear after we take the expectation over p. Also for the second one, the expectation over an edge, ZP, ZQ, is expectation over an edge, sum from j alpha j squared, wjp, wjq. But as before, if you put this expectation inside, and you see the expectation over q, wjq, is actually lambda I times wjp. So this is actually equal to sum of j from 1 to n, alpha j squared times lambda j. So it's weighted sum of alpha j's, and this has to be at least 1 minus epsilon.
Minus 2 epsilon because you're using the.
No, the equation 2 requires. Yeah. But right, because we are saying the threshold rank of 1 minus 2 epsilon is d, this actually implies, well, after the first d eigenvectors, the eigenvalues are all smaller than 1 minus 2 epsilon, so they can't have a large contribution to this alpha j squared. If they have a weight of more than half, then the sum is already smaller than 1 minus epsilon, and that's impossible. So this is essentially saying that sum of j from 1 to n, 1 to d, alpha j squared is at least half. So otherwise, it's impossible to have this to be bigger than 1 minus epsilon. So now we know that a significant fraction of the weight lies in the first D coordinates. So finally, we want to compute the equation 3, but this part is a bit technical if you want to believe me or if you want to see me do the calculations.
What are you going to do in the third part?
So the third equation, the expectation over PQ, this ZP, ZQ inner product squared. The problem is here, these terms, they no longer disappear because we have a square now. So you really have to expand this equation, and it will be a bit messy. So if you, yeah, so the intuition is that the best thing you can do is you just assign weights to the eigenvectors and use these eigenvectors as right. Well, let's say you can assign weights to all eigenvectors and use them as this vectors x1, x2 to xn. So it doesn't help you to mix eigenvectors for x1 and x2, etc. Well, some calculation shows this. And so if you believe me, this is larger than sum of j from 1 to n, alpha j to the fourth.
Is there a way to rotate basis so that it becomes a little cleaner? I mean, can you say that assume the coordinates of the xi's correspond to the wi's or something?
I tried to do that, but it's not clear for me. So. And also because if you can do that, this will be an equal sign, but actually it's greater or equal to. And in many cases, this is strictly larger than that. So
rotation is going to change the notion of what they,
I think if you do a rotation, the first two equations, they are okay, but the third equation, after you take the square, it's not clear whether it will remain the same or it will increase or decrease.
If you rotate the ZIs, everything remains the same, right? If you're rotating the ZIs, everything remains the same. Because the
no, right. If you rotate the ZIs, everything is the same.
What he's saying is, can you rotate the ZIs so that each coordinate aligns perfectly with an eigenvector? And then it's fairly obvious what your alpha is. Are they exactly the scalings of these
yes.
XIs?
Well. Yeah, but the problem is you want to rotate the xi's but not the zi's, but maybe there's a corresponding rotation. Well, anyway, so this is what you finally get if you want to believe me, or okay, so this is more than sum over j from 1 to d. Alpha j to the fourth, then we know this is large, so this must also be large by Cauchy-Schwarz. So this is larger than the sum of j 1 to d alpha j squared over d, I guess. Which is larger than 1 over 4d. So then we proved that this optimal must be at most 4 times d. So this concludes the proof.
So how do this alternate explanation, you've got double less than on the,
yeah, so this one. So if structural rank 1 minus epsilon, notice here, there we use 2 epsilon, but here is epsilon, so here is half epsilon. So if this threshold rank is low, then it's impossible to have vectors, well, they are normalized according to 1, such that if you look at edges, these vectors have high correlation. Their correlation is more than 1 minus half epsilon. But if you look at 2 random vortices, then the correlation is much lower than 1 over d, so this is impossible.
So would you be putting 1 over 4d basically?
Yeah.
So
yeah.
1 over 4d.
So this less than 1 over 4d.
Okay.
Yes.
That's
Yeah. So I'll write the conclusion here.
It's a good breakpoint.
yeah.
Oh, okay. We
Okay,
can.
but if you're finished this section of
Yeah. Let me just tell you the result for the negative eigenvalues, because that's what we are using. But the proof is similar to this. So for negative eigenvalues, the relaxation is actually this obvious is less than minus c. And optimal is at least rank rank minus c of G, and it's at most like 4 times rank minus c over 2 of G over c squared. But anyway, this c will be a constant, so it's within a constant factor of these threshold ranks. Okay, so we can have a break now.
So this, they don't lose the c squared, right?
So we just talk about this relaxation for threshold rank. Now I'm going to show the the idea of the algorithm for this theorem. So as I said, this algorithm requires us to solve SDP with Lasserre hierarchy. But the usual SDP, the SDP in KMS, is about vector chromatic numbers. It's not 0-1 integer programming, so we'll write another SDP. It appears in Eddie's thesis. So this the SDP for coloring. Well, for each vertex, you will have 3 vectors. So for any vertex P, these 3 vectors, VPR, VPB, and VPY. So it means P is colored red, P is colored blue, P is colored yellow. So the sum of these vectors is V0, which is a unit vector. Well, then you say that for every vertex, it cannot be colored by 2 different colors. So VPR, inner product with VPB, and actually all 3 inner products are 0. And for 2 adjacency, for 2 adjacent vertices, P and Q, they cannot be colored by the same color. So VPR, inner product with VQR, is equal to 0, also for blue and yellow. So, well, this is essentially the SDP we use, but we want to apply Lasserre hierarchy. So after k levels of lifting, there are extra constraints. So for every st, s prime, t prime, so they are all a subset of this n times red, yellow, blue. And the union of S and T is the same as union for S and prime and T prime. And the union has sides at most k. So essentially this constraint says probabilities given by a Lasserre hierarchy has to be consistent. So Vs Vt, the inner product should be equal to Vs prime, Vt prime. Later I'll explain why this corresponds to probabilities, and this equation says that probabilities are consistent. What? Non-negativity constraint.
You can say like v comma r dot vq comma b is greater than or equal to 0.
So let's see.
Those are present in Lasserre. I don't think we need.
Yeah, I think for Lasserre you want.
Lasserre does have those.
I don't know. I mean, the usual relaxation I think of would normally include them, but it might be that you don't need them.
Yeah, definitely we want all the inner products are non-negative. Yeah.
Okay.
I think they are somehow implied by those constraints. Okay. Anyway, so for any S and T, Vs Vt inner product is non-zero. Non-negative.
Because you pick two different labels, and you plug them on one side as two different labels, and on the other side you plug the set with both of them in both the sides. So S is, let's say, vertex V1 with color red, T is vertex V2 with color blue, and S prime and T prime have both V1 with color red and V2 with color 2. So the right hand side is positive.
Okay.
Yeah, so I think this is actually implied by Lasserre.
Okay.
Yeah, and notice that here we are somehow abusing notations, because for this VPR, what we actually mean is the set of the set that has only a single element PR. So we call this set N cross RYB. It's a set of atomic events. So an atomic event is just a pair P and PEC. So P is vertex, and C is color. And so as a common interpretation for Lasserre, we interpreted this solution as giving a locally consistent distribution over the vertices. So for Lasserre hierarchy, we know that probability that all events in this S union T happens. This probability is Vs inner product with Vt. And as long as S union T is the same, no matter what S and T you choose, well, they are all the same by this constraint.
You need a sort of longer statement, right? That there exists a local distribution.
Yes, yeah, I'm going to say that. So, okay, yeah, right. So this probability is actually, so there exists locally consistent distribution for any set of at most k events, and the probability is this. Here, this locally consistent means that so the distribution is only over the valid solutions. For example, if you have this graph, then the distribution will be over the valid solutions. For example, this is a valid solution, but the distribution will not have positive weight on something like red, blue. So this will never appear in the distribution. Yeah. So now we have this SDP. So what's the idea of rounding? Well, if you solve this SDP and somehow you are very lucky, you get integer solution, then of course you are done. So for each vertex, you know you have 3 vectors, blue, red, and yellow. So if one of them, say red, has length 1, the other 2 have length 0, then this vertex is pretty much determined. You just color it with red. But of course, normally if you solve this SDP, you won't be so lucky. But it's also good if you, instead of 0, 1, 0, like this is too strong, you have something like 0.2, 0.6, 0.2. I'm claiming that this is also quite nice. So we call this P determined. So if one of VP some color has probability more strictly larger than half, and of course, if it's determined, then we color it with this color C. The claim is if more than n over 4 vertices are determined, then we are already done, because we can color all the determined vertices with color C, and there will be no contradiction. Why? Because so let's say PQ is an edge, and there is a contradiction. So with positive probability that so there's a contradiction, meaning that say, then VPR and VQR, they all have probabilities more than half. But this shouldn't be possible if you look at the locally consistent distribution over these two vertices. Then you will have positive probability that assign red to both P and Q. And this violates the locally consistent constraint.
Sorry, how did you deduce positivity from this?
So the probability for assigning P to be red is greater than half. Assigning Q to be red is more than half. Then the probability of assigning both red is at least some positive value. So if we have a lot of determined vertices, then we are already done. But usually, of course, if you solve this SDP, no vertices will be determined. But luckily, we still have k levels of Lasserre, so we can still do something. So the general idea is, so if you get lucky, then so you have a lot of determined vertices. Then it's great. You are done. So else, well, you still have k levels of Lasserre, so you randomly pick an event W in this set of events. And you condition the solution to this event. So here the conditioning means the new distribution will be the conditional probability of these locally consistent distributions.
So, I mean, just maybe it's related to this point. If you have any set of vectors that's a solution, can't you kind of average the vectors just by rotating the colors?
Yes, but then
Nothing will be determined?
Yeah, then nothing will be determined.
So you get like 1/3, 1/3, 1/3,
Yeah,
third. So
yeah, it's possible
I mean, that
to
seems
get.
like a really, some symmetric solutions are really bad, right?
Right, we don't want symmetric solutions. Also, we can always get symmetric solutions.
Right.
So once you condition on something.
Yeah,
Yeah,
so
once you
the
condition on
point
something,
here
it's
is-
impossible to get symmetric solutions. But before any conditioning, it's always possible to get symmetric.
Yeah, so
solutions.
in some sense, you almost always will. I mean, sorry.
Yeah, it's
typically
much easier
imagine-
to get symmetric solutions than to get lucky or to get a lot of determined vertices. But the hope is, since we have so many levels of Lasserre hierarchy, after a lot of conditioning, somehow vertices become determined. And well, we'll show why this happens.
So just one second. So you picked one vertex at random and one color according to the distribution over the three colors. But you could also pick randomly, assuming it's symmetric.
Yeah, I mean, you might as well.
Okay, I'll explain this conditioning later. It can be done in your way or in some other ways. So this is so this can be repeated. So can repeat. Well, this you can repeat by k times. Well, let me just say it here. Can repeat k times.
So you're adding the conditioning for k distinct vertices Like as you go, or
Yeah. The idea why this conditioning should work is that so intuition is after conditioning, the variance of this solution will decrease at every step. And after conditioning, after the variance is low enough, then you will have a lot of determined vertices. So next time we'll define how this conditioning works and what's the variance and how much the variance will decrease. So this conditioning is you have this solution SDPK, which means it's a solution for the k-level Lasserre hierarchy. You pick a random event W, and so if W always happens by Lasserre, you can actually get a solution for k-1 level of Lasserre where W always happens. Well, also if W does not happen, you can also get SDP solution where W will never happen in this solution. So these are all simple calculations. If W always happens, then you renormalize V sub W to be the V naught, and you renormalize all the other vectors. If W does not happen, you renormalize the other two events as unit vector. So these two solutions can be easily computed. And the locally consistent distribution induced by these distributions will be exactly the conditional distribution. So we have these two distributions, but we pick this by the probability of W. We pick this solution with probability 1 minus probability of W. So as you see, if we pick one of the solutions randomly, then the probability that W happens is preserved. Now I'm going to claim in this, if we pick the new solutions in this way, the variance of events will always drop. So let's take a look. So let W1, W2 be any two events. Let see, R1 equals to probability of W1. R2 is probability of W2. R12 equals to the probability that both events happen. And we want to compute the variance of this variable. So condition on W1, condition on knowing the result for W1, what's the variance of W2? So this is like if we learn the result of W1, what is the average information we get for the event W2? So we can compute this. So variance of W2, condition on W1. So this expression actually means the expectation over W1 then the variance of W2 conditioning on W1 equals to that particular value. So this is R1 with probability R1, W1 is 1. So in this case, the probability of W2 is R12 over R1. So this is a conditional probability. W2 is a 0, 1 event, so its variance is probability times 1 minus the probability. So 1 minus R12 over R1 plus 1 minus R1, R2 minus R12 over 1 minus R1, 1 minus this. So if you simplify this, what you get is this is actually the variance of W2 minus R1, R2 minus R12 squared over variance of W1. So this actually makes sense because, say, suppose W1 and W2 are independent. In this case, knowing W1 should give you no information about W2. But in that case, also this R1, R2 minus R12 is 0, and the variance does not change at all. So we call this term the correlation between these two events. And this correlation actually have geometric meaning in the Lasserre solutions. And that is also why we need to use Lasserre instead of Shirley-Adams. So so this vector is V0, the unit vector. And we have this V of W1, another vector V of W2. So we know that this part is exactly R1 because it's a probability. And this vector, which is orthogonal to V0, we call it U of W1. Again, this part, this is R2. And this vector we call U of W2. Now we look at the inner product of UW1 and UW2. It's R2 because the probability is exactly the inner product of VW2 and V0. So it's the length of this vector VW2 is actually square root R2 because its inner product with itself is also the same thing. But that's not important for us now. Now we are going to see the inner product between these two vectors, UW1 and UW2. Well, this inner product is equal to the inner product of VW1 and VW2. But so VW1, VW2, they have R1 times R2 in this dimension, and UW1 dot UW2 in the rest of dimensions. So it's this minus R1 times R2. But what is this? This is exactly R12. So it's R12 minus R1 R2, exactly equal to that. So if we just take the square. So so we shall define the correlation of W1 and W2 to be the inner product of UW1, UW2 squared. And the variance of a solution variance of this SDP to the k is expectation. It's the expected variance of random event W in this solution. And we call the global correlation of this SDP to the k is the expected correlation of two random events. So then we want to show when variance shows this lemma. So we get this SDP k minus 1 by picking a random event and conditioning on that event. So variance, well, the expected variance of SDP to the k minus 1 is at most the variance of SDP to the k minus 4 times the global correlation. So this means the variance will always decrease by the global correlation, and if global correlation is always high, soon the variance will be reduced to some very low value, and things will become nicer.
So, intuition on where are you going to go through by the 4, or?
Yeah, 4 is actually, yeah, I'm going to prove that. Oh, I need to, yeah. Yeah, it's actually, you look at this equation, the variance of W1 is at most 1/4 because it's a 0-1 event. So that's where the 4 is coming from. So that's essentially the proof. Okay, so so now you see, as long as we can, well, as long as the global correlation is high, the variance will be reduced, and when variance is very low, as most of the vertices will be determined. Because if a vertex is not determined, its variance will be quite large. Okay, so there's a simple lemma that says if variance is small, then at least n over 4 vertices are determined. This is simple because vertex P, if it's undetermined, then the variance of P red plus the variance for the other two events over 3. This is at least, well, 1/4 plus 1/4 plus 0 over 3, which is 1 over 6. Because the worst case happens when P has probability 1/2, 1/2, 0. If it's 1/3, 1/3, 1/3, then this variance is even larger. So if it's undetermined, the variance is always large. If the expected variance is low, then we must have a lot of determined vertices. Now we want to prove that global correlation is always high, and as you can guess, to prove the global correlation is high, we need to use this relationship with threshold rank. To do that, we will construct these vectors Z and show that they have local correlation. Well, the Z vector is actually the concatenation of the U vectors, UPR, UPB, UPY. So the Z vector is a concatenation of these U vectors. So now you see ZP times ZQ. So we need to prove for edges they have high correlation. So we look at edge, P is adjacent to Q. Then we know UPR, UQR. This is equal to VPR, VQR minus the probability of PR and the probability of QR. This is as before, but this is 0 as the SGP mix. So this is minus the product of the probabilities. Now you see that ZP, ZQ. Okay, so we have this P and Q. If one of them is determined, then we don't care. But if all of them are undetermined, then we want to show that the ZP inner product with ZQ is smaller than minus 1/4. Well, this is simple because this inner product is minus the probabilities. So the worst case happens when P has probabilities like half, half, 0. Q have probabilities like 0, half, half. And then the sum of products of probabilities will be 1/4, and this is minus 1/4. So this is a worst case. But we know that there are only, so now either we have more than n over 4.
This was for regular graphs.
Yeah, this was for regular graphs. Yes. So case 1, we have a lot of determined vertices. In this case, we are already done. But the other case is the determined vertices is there are very few determined vertices. But because this is a regular graph, if you have only 1/4 of determined vertices, at least half of the edges will be between undetermined vertices. Because, well, each edge, one of its endpoint has to lie in this set. So half of the edges will have this inner product is at most 1/4, which means the expectation over random PQ, ZP, ZQ is greater than, is smaller than minus 1/8. So this is already satisfying equation 2. well, these vectors Z, they are not unit vectors, but they are very close to unit vectors. The norm of Z is actually 1 minus, well, because UPR norm squared is 1 minus the probability of, let's see, so the norm of ZP is the sum of the norms square of this UPR, UPB, UPY, and then is if you compute it, it's actually 1 minus the probability of PR squared minus the probability of QR squared. Sorry, PB squared minus probability of P yellow squared. So this is always smaller than 1. But if it's undetermined, this is also at least 1/4. So the ratio between, so if you want to scale them to satisfy 1, the ratio you need to scale is a constant. So that's not a problem. So now we have these vectors. They are roughly normalized. They have local correlation. So by this theorem, we know it must have high global correlation. That is, if you pick random PQ, ZP, ZQ squared is large. It's larger than omega 1 over d. But this value, notice that global correlation is defined that way, but this value cannot be much larger than the global correlation just by a simple calculation. Because ZP times ZQ, ZP inner product with ZQ is just UPR times UQR. So all those terms appear in the definition of global correlation. So we know the global correlation is also at least omega 1 over d. So roughly in one step, either you are finished because you have a lot of determined vertices, or if the number of determined vertices is small, then you can always prove that the global correlation is high and variance is decreased by at least 1 over d. So after a constant times d steps, you will reduce the variance to be smaller than 1 over 8. And there you will always have at least n over 4 determined vertices. And the theorem is proved. Okay, we are almost out of time. Is this proof clear, or should I?
So you've got a number of determinant vertices. Oh, I see. You're just going to pick the colored vertices. Yeah, sorry. Go ahead. You've colored actually n over 4 vertices.
Yes. Yeah, but the theorem just says an independent set of size n over 12. But yeah, but actually you will just use the partial coloring for n over 4 vertices.
Always we are concerned only about the same graph G's. We never talk about subgraphs of G. I mean,
Right.
Because the threshold rank needs to be, we only have a condition on threshold rank of G and we don't know about.
Yes, so that's why the conclusion is you can find an independent set, but not you can find a coloring. Yeah, so you find this independent set, you remove it, but then, right, it's not clear whether the threshold rank of the subgraph is still low. That's why this is not coloring algorithm. Another thing is this theorem, as I stated here, only works for a regular graph, but it's not. The thing is, G doesn't have to be a regular graph, but you can arbitrarily weight the edges of this graph G. So you have graph G, you assign weights to the edges, so that after the reweighting, this graph is now a regular graph. Now, so you call this matrix M. M is weighted adjacency matrix of this weighted graph. If the threshold rank, the threshold rank of M is low, is D, then the theorem still holds. Threshold rank for this matrix M is still the number of eigenvalues smaller than -1/16. So, right, we don't really need a regular graph, but instead we need one of the reweighting of the graph so that the threshold rank is low. Yeah, we were hoping to extend this to a coloring algorithm by, so if you can prove a certain conjecture, for a graph G, for any graph G, either there exists a reweighting M, so that the threshold rank is low. Then in this case, we will apply our algorithm and find a large independent set. Or you can find, or there exists a set S such that the vertex expansion of S is at most n over size of S to the 1 minus C. So here we generally think D as some n to the epsilon and C as a constant. So if this conjecture is true, then you can always color a graph with n to the 1 over C, essentially.
What about the Blum coloring tools at all here?
No, I haven't talked about.
Then it would make more sense.
Yeah. So Blum coloring tools is a set of tools to color 3 colorable graphs. So to make progress towards FN coloring, you either find a large independent set, which we have already been using, and this is easy to understand, or you need to find a set S that has low vertex expansion. In that case, you will throw out all the vertices of all its neighbors, and you recurse on this S. The third case is you find 2 vertices that has to have the same color. For example, if these 2 vertices, they will have to have the same color, and you can merge them. So this is like using the second condition of the Blum coloring tools. So for a graph, either you have low threshold rank, so you can directly apply our algorithm, or you can find this S that has low vertex expansion. Then what you do is you find this S, you remove all its neighbors, and you recurse on S and this S complement. By doing this, you will eventually get something like n to the 1 over C coloring. So we don't have counterexamples for this conjecture. We know this is not true when d is smaller than polylog, but when d is polylog, we don't have counterexample.
What do you mean by that? Exists an M such that the rank is?
So M is reweighting of the edges of the graph G, so that G is now a regular graph.
Also, what is the notion of expansion you're using here?
Right. The definition of vertex expansion of S is the neighbor of S minus S divided by the size of S.
Okay. So then, I mean, the conjecture states that, I mean, the number on the right is something larger than 1.
Yes.
And
So vertex expansion can can in general be larger than 1. Yes. And also the degree of this graph will be very large. If degree is low, you can just you throw out low degree vertices. So if it's a random graph, for example, then you will always have high vertex expansion, much higher than what I wrote here.
Two questions. One, like when threshold rank is low, does
Yeah.
eigenspace enumeration give you anything at all?
When threshold rank is low, eigenspace enumeration gives you, but what do you expect by eigenvalue enumeration? Because when threshold rank is low, we can already apply our algorithm to find this large independent set.
Yeah, but I mean, like for example, in unique games, sort of the Lasserre hierarchy is also a thing which captures the eigenspace enumeration algorithm, right? It's
Yes.
sort of an alternative. Does this also hold here, or here it's strictly better to use this algorithm?
Yeah, I think here it's strictly better to.
Second, and so this notion that you define is sort of a general notion, right? Given a graph, over all reweightings M, what is the minimum threshold rank that you can achieve?
Yes.
So can you even approximate this? Like what is the minimum threshold rank you can get over all?
What is the minimum or what is the maximum?
I'm sorry?
What is the
Minimum.
maximum of all these thresholds?
No, what is the minimum over all the threshold rank?
You want to reduce the threshold rank to as low as possible.
But
Yes, that can actually be approximated. So there were works for like fastest mixing Markov chains where they try to assign, but that's only for the second largest eigenvalue. But also there are works about say first k eigenvalues, so it can be approximated. But there's no, I don't know what exactly the value you'll get, but there's an algorithm that can approximate this value.